Hi, we're doing analysis of algorithms. We're up to chapter 4. We're doing the homework problems in chapter 4 that we were assigned. Okay, these are not hard problems, just some things to think about. So, for section 4.1-1, the first problem, what does find maximum subarray return when all the elements of A are negative? So, in terms of stock markets, what happens if you're losing money? What's the smallest amount that you can lose money? Anyways, the algorithm works the way it should work, namely, well, the truth is, if all the numbers are going down, you shouldn't invest at all. But finding the largest maximum subarray, the way that algorithm works is it's going to choose the smallest, and by that I mean the smallest negative number. Okay, so, but I just want to show you something here. Okay, let's say this is negative 21, this is negative 1, this is negative 2, let's say, and this is negative 13. Okay, so we compare three things when we're doing this. We split it in half, we look here. What's the smallest subarray here? And that's going to be negative 1. Okay, then we're going to look at this, and that's going to be negative 2. Negative 2 is the smallest number. It's the maximum number. Okay, but then the third thing is we're going to go like this and get those things that cross, and it's going to be minus 1 and minus 2. Okay, now minus 1 plus minus 2, so what's the smallest of all three of these? That's going to be minus 1. Okay, so from all three of those, the smallest thing here is minus 1. The smallest thing here is minus 2. The smallest thing that crosses, when it crosses, it must take that, and it must take at least one thing here and one thing here. So that's going to be minus 1 plus minus 2 is minus 3. Anyways, minus 1 is the smallest negative number, and it's going to do that one. Okay, that takes care of that. Okay, next, section 4.1-2. We did this in class, but it's worth to see it again. Write pseudocode for the brute force method of solving the maximum subarray problem. Your procedure should run in O of n squared time. Okay, and we did it in class, but it's worth doing it again because it's a nice algorithm. So let's call it max subarray. Okay, and let's say an array of numbers is entered, and what you want to do is you want to have a variable called max sum. Okay, and it should start off as negative infinity. Okay, and then you want to try all starting places and all ending places. For I equal 1 to A dot length, for J equals I plus 1. In other words, you're going to start buying it on I. You're going to look for a proper selling place for at J to A dot, okay, this I guess is minus 1 to A dot length. Okay, that's your potential selling place, and then what do? You compare, and it goes as follows. If A of J minus A of I, okay, that's the spread, the difference between when you're selling it to when you're buying it. In other words, if you buy it here and you sell it here, how much money did you make? Well, if that is greater than max sum, that's your thing, then max sum is equal to A of J minus A of I. In other words, that's how much money you're going to make, okay? But there's another two things you should do. You should write buy is equal to I, and sell is equal to J. You got to keep that in memory, go through the whole thing, and then of course when you finish, return buy and sell. Okay, so that takes care of that. So basically, you're going through the array. Here's your I, and you're going to try all possible j's. Then you're going to go I plus 1, you're going to try all possible j's. And then you're going to go I plus 1, all possible j's. Each time keeping track of what the spread is and looking for the maximum spread. So it's a nice algorithm. How much work is done? Well, basically this does about n for n number of elements in the array, and this does n minus 1, n minus 2, this does n minus 1, this does n minus 2, n minus 3, and n minus 4, etc., etc. And we did this with the Gauss trick, and it turns out it's about n times n over 2, which is theta of n squared. So that takes care of that. Okay, so that's section 4.1. Okay, now let's go on to section 4.2. Okay, and this is using Strassen's algorithm. Okay, and there's nothing to talk about here. Strassen's algorithm is just a trick, but basically they want you to do Strassen's algorithm on a 2x2 matrices. So 1, 3, 7, 5, okay, times 6, 8, 4, 2, okay. And I'm not going through Strassen's algorithm, but I'm going to list off the procedure of doing it. And again, there's no brains here. It's just writing down the formulas for Strassen's algorithm and getting it straight. Okay, so let's write it. So this is A and this is B, and it goes as follows. S1 is equal to B12 minus B22. So B12 is 8 minus B22 is 6. So this is 6. S2 is equal to A11 plus A12. Let's do that. That's 1, 1 plus 1, 2 is 4. Okay. S3, I'm going to get bored of this in a second. No, I'll probably finish it. A21 plus A22. Okay, and that's equal to 12. That's these two. Okay. S4 is equal to B21 minus B11. It's this minus this, which is -2. Okay. S5 is A11 plus A22. That's this plus this, which is 6. Okay. I'm going to let you write down the rest, what the formulas is. S6, S7, S8, S9, S10. Okay, 6 is 8, 7 is -2, 8 is 6, 9 is -6, 10 is, let's write it out, B11 plus B12, okay, which is, let's do that, that's 6 plus 1, 2, 6 and 8 is 14. Okay, that takes care of that. And now, we're not finished. Okay, so now you have P1, P2, P3, P4, P5, P6, okay, and this is equal to A11 times S1. Okay, so S1 is 6, A1 is that, is 1, so that's equal to 6. Let's do a few more. This is equal to S2. You're getting these formulas from the book. You're getting the numbers from here. P2 is equal to S2 times B22. Okay, S2 is 4, B22 is 2, so that's an 8. Okay, P3 is S3 times B11. S3 is 12, B11 is 6, 6 times 12 is 72. Okay, I'm just going to fill in the rest. You can figure it out yourself. It's going to be minus 10. This is going to be 48. And this is going to be minus 12. That gives you the P matrices. What a pain in the neck. Okay. And then you finally have the C matrices. Remember, A times B equals C. So we're going to write the C matrices over here. You're going to get C11 is equal to P5 plus P4 minus P2 plus P6. Okay. Notice there's no multiplications here. There are 7 multiplications here. That's the point. In this thing there are 7 multiplications. By the way, we should check that there are 7 multiplications. 1, 2, 3, 4, 5, 6. I only see 6, but that's okay. There should be 7 someplace. Okay. Anyways, let's do it. P5 plus P4, 48. Plus minus 10 is 38. Minus 8 is 30. Plus P6 plus 30 plus minus 12 is 18. So that's 18. Okay. C12, okay, is equal to, you got to follow the formula, which is in the book, P1 plus P2, which is equal to 14. 6 and 8 is 14. Okay. Okay, let me just tell you the rest. C21 is equal to 62, and C22 is equal to 66. Okay, we're going to put these numbers in, and we get 18, 14, 62, 66. Okay, and there's a very easy way of checking that I did it right. 6 times 1 is 6 plus 4 times 3 is 12 is 18. Let's do this. 8 times 1 plus 2 times 3 is 8 plus 6 is 14. 6 times 7 plus 20. 6 times 7 is 42 plus 20 is 62. Great. 8 times 7 plus 2 times 6. So plus 2 times 5 is 66. So that takes care of that. Again, it's a trick that Strassen was able to see. The main point is there are less multiplications in here than before. Okay, so that's section 4.2. Okay, we are skipping section 4.3. We are skipping section 4.3, but we are doing section 4.4, and that is the hardest part of this chapter. Okay, so let's do it. Section 4.4-2. Okay, and we're going to write, use a recursion tree to determine a good asymptotic upper bound to the recurrence T of n equals T of n over 2 It's 1. There's a 1 in front of it, plus n squared. Okay, so let's build a tree. First, a node with one thing. Then, this tree is only going to have one node each time. So this becomes n squared, and this becomes t of n over 2. Okay, and we continue building this tree. This becomes n squared, and this becomes n over 2 squared, and this becomes t of n over 4. And it goes on. So this becomes n squared, this becomes n over 2 squared, this becomes n over 4 squared, okay, dot dot dot. It's pretty simple, so we'll just do it quickly. This becomes n over 8 squared, dot dot dot. Okay, there's going to be a 1 over there. Okay, so first question, we do this just like we did it in the book. First question, how tall is this tree? And the answer is log n, log base 2 of n, because you're splitting it into 2. How many times can you split n into 2? Answer, how many times can you split n by 2? Answer, log base 2. Okay, so that takes care of that. Okay, and now we're going to have to find some patterns here of what it looks like. So basically this is, well, let's leave that alone. So this is n over 2 to the 1, 2. Okay, and this is n over 2 squared, squared. And then this is n over 3, 2 to the 3rd squared, dot, 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 dot. Okay, great. Okay. Okay, I want to do it another way. So this is, by the way, this is n squared. This is n squared. So I want to write it another way. I want to write it as, this is equal to n over 2 squared is 4. This is going to be 4 squared is 16. So it's going to be 4 to the 16. This is going to be 16. 2 squared is 4. Squared is 16. So I'm going to write this as 4 squared with an n squared on top. Okay? And this is going to be 8. This is going to be 64. So another way of writing that is 4 to the 3rd n squared. Dot, dot, dot. Okay? In general, it's going to be n squared divided by 4. Here's 4 squared. Here's 4 to the 1. Here is n squared divided by 4 to the 0th power, which is 1. Okay? So each one is, this is going to be, the general case is 4 to the I. Okay? And now we add up all these numbers. So basically, what do we have? We have the sum of I equal 0, that's the lowest exponent, to log base 2 of n squared divided by 4 to the I. The rest is math. Okay, first thing first, take the n squared out. Okay, then we're going to do the geometric series. So let's do it. You ready? So this becomes this. N squared. I equals 0 to log base 2 of n of. I'm going to write it as follows: 1 over 4 to the ith power. this is geometric theory. This is perfect geometric series. So this is n squared times 1 over 4 to the log base 2 of n plus 1 minus 1 divided by 1/4 minus 1 is minus 3 over 4. Okay, 1/4 take away 1 is 1/4 minus 4 over 4 is minus 3 over 4. Okay, I'll just make sure I have this right. Okay, so close. Okay, I'm going to bring this to the top. I'm going to flip this and put this on, so we get minus 3 over 4. Uh-oh, what do we do with that? I'll figure it out. Okay, I'm sorry. So this becomes minus 4 over 3 n squared times, okay, put that 1/4 over there. That's going to be 1/4. I'm going to swap these two, and this is that trick I taught you about. Okay, this and this is going to swap places. Okay, so we're going to get as follows. So that's going to swap places. So it's going to be n to the log base 2 of 1 over 4. Okay, and we're going to press pause for a second. Okay, so the 1/4 comes from that plus 1. Then we have this log of n. Okay, sorry. Should be this red. Not neat. Okay, next. So we swap these things. The n, okay, and then there's a minus 1. Very good. Okay. Okay, great. Okay, let's just do this. What do you have to raise 2 to in order to get 1/4? So just remember, 2 to the minus 2 is equal to 1 over 2 squared. Which is equal to 1/4. Okay, so the answer is minus 2. So this becomes as follows. Minus 4 over 3 n squared times 1/4. Okay, and this becomes n to the minus 2. So this becomes n to the minus 2. Okay, let's write n to the minus 2 another way. So this becomes 1 over n squared. Okay, minus 1. Okay, so let's multiply out everything. So this becomes, the 4 cancels out with the 4. Okay, and so this becomes n squared, and the n squared goes out. Okay, so let's cancel this out. 4 goes with 4, n squared goes with n squared. Okay, and so you're left with minus 1 over 1/3, I think. Minus 1/3, but don't forget, we have to multiply this minus 4, so it's minus 1 times minus 4, 3, so this becomes plus 4 over 3 n squared. Okay. Okay, so that's it. So it's a number minus 1/3 plus 4 over 3 n squared. Anyways, leading coefficients are not important. Adding numbers is not important. And this is equal to theta of n squared. That's it. Okay, we have to, let's go through it again. Geometric series. Add the 1 minus the 1 divided by 1 over 3 over 4. We bring this minus 3 over 4 to the top over there, so we did that. Okay, the plus 1 here means another 1/4, so we put that 1/4 over there. Then we have this trick. When you have something down here and that, we swap it, we make the n to be on the bottom, and that's helpful. Now this is a number. We calculated that number to be minus 2, so we put it down here. And then we simply multiply it out. The 4 cancels out with the 4. The n squared cancels out with the n squared. We're left with 1/3 with a minus. That's it. Okay, but we take this entire thing and we multiply it on the side. Minus 1, that becomes plus. Minus times minus is plus. 4/3 n squared, we have that. Okay, this is unimportant, this is unimportant, you're left with n squared. Finished. Okay, next. Okay, next is 4.4-4. Tn is equal to dash 4. Tn is equal to 2 times t of n minus 1. Tn equals 2 times t of n minus 1. We're going back to my examples. We're doing minus 1 instead of dividing by something. Okay, plus, I think 1. Plus 1. Okay, so the trees here are going to be of size n, of size 1. So basically it goes as follows. T of n. Start your tree. Okay, then make a 1 out of it, and it has 2 children, each of t of n minus 1. T of n minus 1. Okay, good. Next, you're going to have a 1 over there, and you're going to have 2 children. This becomes 1 with 2 children, t of n minus 2. T of n minus 2. This is again a 1 with 2 children, t of n minus 2. T of n minus 2. Okay, let me just make sure it's coming out nicely. Okay, not the neatest thing, but fine. It's not a neat thing. Okay, and then you're going to have dot, dot, dot. You're going to have 1, 1 and 1, 1 and 1, 1 and 1. Each one is going to have 2 children. Okay, and we go on. Okay, question. How tall is the tree? We always ask the same questions in the same order. Answer, we're not dividing by 2 here, we're subtracting. So you're going from n to n minus 1 to n minus 2 all the way down to t of 1. So this is going to be size, let's say, n minus 1. Okay, how much is added at each level? Well, here you're going to have 1, here you're going to have 2, here you're going to have 4, here you're going to have 1, 2, 3, 4, 5, 6, 7, 8. Get a pattern, here you're going to have 16, etc., etc. Okay, so let's write this another way. This is 2 to the 0, this is 2 to the 1, this is 2 to the 2, this is 2 to the 3, this is 2 to the 4, this is dot, dot, dot. In general, you're going to have 2 to the I. Okay, so now we simply add it up. Sum, because we want to count how many is in total in this entire Christmas tree. And so we have the following. Okay, I equals 0 to 2, to n minus 1. Because that's how many levels we're doing. That's how deep the tree is. So I equals 0 to n minus 1 of 2 to the I. This is the simplest example of the geometric series. Okay? We did this in class, this geometric series. Just want to make sure that I have it right in terms of n, not n minus 1. Hold on. Don't move, don't move. Okay, sorry, I think this should be n. The height is n, because okay, and so we do that. Okay, and this is equal to 2. to the n plus 1 minus 1 divided by 2 minus 1. So this is equal to 2 to the n plus 1. Okay, minus 1. I think that's it. Okay. If you want, you can write this as theta of 2 to the n. Because 2 to the n plus 1 is 2 times 2 to the n plus 1. So it's 2 to the n plus 1 is 2 times 2 to the n. So that takes care of that. Okay? So you're just adding up a geometric series. Great. Next. The next one is 4.4.6. 4.4-6. T of n is equal to, it's a funny little thing, but we'll do it together. T of n divided by 3. Okay, plus 2n c times n. Okay. So this is funny because your tree is going to be lopsided. You'll see in a second what I mean by that, but the tree will be lopsided. Okay? So let's do it. You know what? I'm not going to make the tree like I usually do, 1, 2, 3. I'm going to start it from the top, and I'm going to use my eraser. You can't use the eraser. You have to write. Well, let's do it. So it's going to start off as T of n. Okay? And that's going to turn into C times n. And he's going to have 2 children. So let's just write C times n. Okay? One child is going to be T of n over 3. And the other child is going to have 2n over 3. Okay, great. Now, when I plug this one in, I'm going to get C times n over 3. Okay, and he's going to have 2 children. One child is going to be C times n over 3. I'm plugging in n over 3 in here. I'm going to get n over 9. And here, I'm going to plug in n over 3 in here, and I'm going to get C times 2n over 9. Okay, that's good. Okay, but what happens when we do this? Let's think about it for a second. What happens when we do that? Okay, now we're going to erase this, and we're going to put in his 2 children. So this is C of 2n over 3. Okay, and he's going to have 2 children. Now here's where it gets more interesting. So we're plugging in 2n over 3 in here. Okay, and so now we have, if n is equal to 2n over 3, what does this become? And the answer is it becomes C of 2n, n over 9. Plug in 2n over 3 over here. This becomes 2n over 3. The 3's become 9. But here it becomes plug in 2n over 3 here. This becomes 2 times 2n over 3. And the 3. So this becomes 4n over 9. Okay? Great. Now, when you go on, it gets more interesting. Plug in n over 9 over here. This becomes n over, let's forget about the c's, n over 27. Okay, and this becomes 2n over 27. And this becomes, plugged in n over 9 here, and I plugged in n over 9. Now I'm going to plug in 2n over 9, so this becomes 2n over 27. And this becomes 4n over 27, and this becomes, when I find his 2 children, this is going to become 2n over 27, and this becomes, I think, 4n over 27, and this becomes 4n over 27, and this becomes 8n over 27. Plug in 4n over 9 into here, and you look over there. So it's going to be 2 times 4 is 8, and over 3, so that becomes like this. Okay. Okay. Rather than going further, we can go further, but it'd be a pain in the neck. But rather than doing that, let's look at what the depth of the tree is. Okay? Now, that has two answers here. Well, it depends. Okay? And it's not even clear over here. But if you look at this side, what's the depth of the tree here? So you start off with an n over 3, n over 9, n over 27, dot, 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 dot. How long is this side of the tree going to be? And the answer is, well, if every time you're dividing by 3, how many times can you divide by 3? And the answer is log base 3 of n. That's fine. That's the easy part. Okay? Now ask another question. How long is this side of the tree? That's a little bit more complicated. I want to write this in a different way. I want to write this as t of n divided by 3 over 2. So look what we're doing here. We're dividing by 3 over 2. We have n, we divide by 3 over 2. We divide by 3 over 2 squared. We divide by 3 over 2 to the third power. Dot, 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 dot. So, question, how long is this side of the tree? And the answer is log base 3 over 2 of n. Okay? So, that's the way the tree is. The tree is a little bit lopsided. Here's log base 3, this is log base 1.5. Okay, question. Which side of the tree, which is a shorter side of the tree? And the answer is, here you're always dividing by 3. Here you're dividing by 1.5. Which way are you going to get to the bottom quicker? When you divide by 3, you're going to get to the bottom quicker. Here, you're only dividing by 1.5, you're not going to get to the bottom quicker. Okay, so let me show you what this tree looks like really. A big version of what this tree really looks like. This tree really looks something like this. All the time we had a Christmas tree, but here it looks like this. Okay, and the answer is this is log base 3 of n. This is log, rather than 4 over 3, I'm going to write it as 2 over 3. I'm going to write it as 1.5 of n. Okay, so that's where it goes like that. Okay, now let's go back to the question. It says as follows. Is n log n, argue that the solution, okay, the thing that they want you to do is say as follows. This tree, if you added up the numbers, just cut it off over here, you'll get something, okay? And what they're showing is if you follow this is the height, and if you do adding up level by level here, you're going to get n log n. That's very nice, okay? But they want to say, they don't want to know just this part of the tree, they want the whole tree. So that what they want you to do is say, oh look, this whole tree is bigger than n log n, because you have this extra stuff there. Okay, so this means it grows larger than or equal to n log n. So again, this part of the tree itself is n log n, but then when you add in this extra stuff, you get a lot more. Okay, so that's what they're doing. Okay, so it's a nice thing. It's a little bit more complicated, but notice because there's two different unequal things, the trees turn out a little bit lopsided. Great. Okay, let's finish off by doing section 4.5. 4.5 is fairly simple because it's the master theorem. We love the master theorem because it makes things much more easier to deal with. So let's deal with that. Okay, I'm going to do a little bit quickly because the master theorem is pretty simple. I mean, applying the master theorem is pretty simple. Okay, so 4.5-1. Okay, there's 5 different problems. We're going to do them. Okay, t of n is equal to 2 times n over 4. T of n is equal to 2 times t of n over 4 plus 1. Okay, so let's go through it. A is equal to 2, B is equal to 4. Okay, log base B of A is equal to log base 4 of 2. How much do you have to raise 4 to in order to get 2? And the answer is, if we raise it 2 to the half, so this is 0.5. Okay. In contrast, f of n is equal to 1. Okay, and which one grows faster, which one grows slower? And so we just have to follow that thing. So we conclude that t of n is equal to theta of n to the half. Okay, that's part A. Okay, part B. I'm doing it a little bit quicker. Okay, let's do B. B is t of n equals 2 t of n over 4 plus square root of n. Okay, so let's go through this. A is equal to 2, B is equal to 4. Okay, log base B of A is equal to log base, the same thing we did that before, of 4 of 2. It's the same thing, just there's a square root. Okay, here f of n is square root of n. We compare the two, and we use the middle case of the master theorem. T of n is equal to theta of n to the half times log n. Okay. Great. Let's do number C. I can erase, you can't. This is plus n. Okay, we got the same thing. So this is plus n. Okay, and now we have the third case, and basically the third case says t of n is equal to theta of n. That takes care of that. Okay, so that's 3 different examples with the same a and b, okay, but with different functions, and we want you to see both possibilities. Okay, d is n squared. Okay, so let's do d. Okay, this is n squared. Okay, again, a and b is the same. Okay, and here we have t of n is oh, I'm sorry. Oh, I'm sorry. T of n is theta of n squared. So this is again case number 3. Okay, good. Next. Okay. do this. Section 4.5. Here's a long question, but it's worth doing. Professor Caesar wishes to develop a matrix multiplication algorithm that is asymptotically faster than Strassen's algorithm. So we talked about Strassen's algorithm, and let's just write up what we know. Strassen's algorithm is theta of n to the log of 7, log base 2 of 7. Okay, n to the log base 2 of 7, which is fine. Okay, his algorithm will use, instead of dividing into 2 by 2, it divides it into sizes of n over 4 by n over 4, and determines and the divide and combine steps will take a theta of n squared time. He needs to determine how many subproblems his algorithm has to create in order to beat Strassen's algorithm. If his algorithm creates a subproblems, then the recurrence of the running time, t of n, becomes as follows. So let's just remember what Strassen's was. Strassen's was t of n equals t of n over 2, we split it into n over 2, plus theta of n squared. Okay? But the main point is we had a 7 here. Okay, great. Now the guy who wants to do it, does it as follows. T of n is equal to a of t of n over 4 plus theta of n squared. So everything is exactly the same except this. So here's the question. What does a have to be in order for this thing to beat Strassen? That's the question. Okay? So we're going to stop for a minute, and you're going to try to think of it, and then we'll answer. Okay, so the way to do this is as follows. We have to compare log base 4 of a, that's to get this thing, versus log base 2 of 7. Okay, and what we want when we do this is that as long as this is true, then this outcome will be better than this outcome. Okay, and the way we have to do it is a has to be less than, if you solve for a here, you have a is less than 49. If it's 48 or anything less, then it beats Strassen. Okay, you can raise this to the 4th power, you can raise this to the 4th power, so this is 4 to the 2.7 or something like that. 4 squared is 16. 4 to the 3rd is 64. So you get that. If a is less than 49, you win. Okay, we can do it with a calculator if you want, but I don't have a calculator. Anyways, the point is, as long as a is less than 49, then this new thing beats that. Okay, last problem. Last problem is is 4.5-3. Use the master theorem to show that the solution to the binary search recurrence t of n is equal to 1, t of n over 2 plus 1 is whatever. Anyways, it's the simplest thing in the world. We did it actually in class, but let's do it again. T of n is equal to, how do you do binary search? You do one operation, and then you're left with t of n over 2. Let's fill in, let's use the master theorem. So a is equal to 1, b is equal to 2. Log base b of a is equal to log base b of a is equal to log base 2 of 1. What do you have to raise 2 to in order to get 1? And the answer is 2 to the 0. Okay, so the answer is 0. Okay, so now you can compare log base b to the a and 1. Okay, you have to compare those two. Well, this is equal to n to the 0, so that's actually equal. And so there you use the middle case of the master theorem, and so the answer is t of n is equal to theta of 1 times log of n, which is equal to theta of log of n, which is exactly what the binary search works. Okay, so that takes care of that. Okay, so we did all the problems from chapter 4, and we hope you gained something from it. Have a wonderful day.